Here I've got a nice appearance of the golden ratio, and it's due to George Phillips Odom Jr., who was not a mathematician, but was instead an artist who was very interested in finding the golden ratio, not only in art, but in nice geometrical figures like we have right here. Okay, so let's see our setup. We have an equilateral triangle ABC, and it's inscribed in a circle. So here's my picture. So I've got equilateral triangle ABC and then the inscribing circle. And then from here, we want to find the midpoint of AB. And so we'll call that D, and that's about right here. So there's D. Then we'll find the midpoint of BC, and we'll call that E. So that'll be about right here. So that's E. So let's see, what does that mean? Since these are midpoints of these line segments, we know that this length is the same as this length, but since we have an equilateral triangle, that's the same as this length and this length. Furthermore, if we complete this triangle down here, that's going to be the same as this length. So in other words, the side length BE is the same as side length DE, BD, DA, and maybe EC as well. So now what do we do from here? Well, I'm going to take this line segment DE and extend it until it intersects with our circle. I'll call that intersection point F. And then I'll also extend it back this way, and I'll call this intersection point G. And then that allows us to state our goal now that we have this fully completed figure. And so let's do that. Our goal is to find the ratio of two line segment lengths here. Well, that should make sense because I said that this was about the golden ratio. So we should probably be finding the ratio of something. And we'll find the ratio of side length DE over side length EF. So that ratio. So DE would be this right here, and EF would be this right here. Okay, so how can we start to approach this? Well, let's notice that chord BC and chord GF intersect. And there's something called the intersecting chords theorem that will say something about the lengths that are built out of these intersections. But we can derive that theorem pretty easily using some more basic results. So to get at those more basic results, I need to introduce some more line segments here. So I'll first introduce the line segment CG. So that'll go about like this. Okay, so there's line segment CG. We're also going to need line segment BF. So let's introduce that as well. Okay, great. And now we can start applying some standard results. So the first will be using the observation that angle BCG subtends this arc BG, and angle BFG subtends the same arc. So that means that these angles are congruent. So I'll just put like little symbols there to mean they're congruent, and then I'll fill that in over here. So we see that measure of angle BFG is the same thing as the measurement of angle BCG. Then we can see that these angles are opposite of each other. And so that means that those are congruent as well. So I'll put like a triple hatch here to show that those angles are congruent. So let's see, that's angle BEF. So I'll write this, measure angle BEF is the same thing as measure angle DEC. So measure angle DEC. But now if we look at this a little bit more carefully, we see that this triangle BFE has exactly the same angle measurements as this triangle, we'll call it ECG. Well, there's one missing angle from each of these triangles, but using the sum angle formula to 180 degrees, we'll fix that pretty easily. So let's write that down. We have the triangle BFE is similar to triangle, let's see, it was ECG. And now that we've got this result involving similar triangles, we can start to write down some ratios involving the sides. So let's do that. So there are several different ratio relationships that we could write down, but the ones that will be useful for us are GE, or the length of line segment GE, divided by the length of line segment BE. So let's see, that's the quotient of this side right here with this side right here will be the same thing as the length of line segment EC divided by the length of line segment EF. So that would be like this one right here with this one right here. Notice that those are corresponding sides in each of these triangles. And from here, we can actually derive the quadratic formula for our goal ratio that is well known to be satisfied by the golden ratio. Okay, so let's do that. So where can we go from here? Well, we can take this GE and write it as DE plus DG, but we know that DG is the same thing as EF. So we can, in fact, write this GE as DE plus EF. So let's do that. DE plus EF over BE. But let's notice that BE, because it's a side of an equilateral triangle, is the same thing as DE. So we'll write that instead of BE. And now we look at EC, but since this was a midpoint, that's the same thing as DE. So we'll write this as DE, and then we'll leave the EF alone. Okay, so we've got something like this. But now we can do a little bit of simplification. We have this is 1 plus 1 over DE over EF equals DE over EF. But now we can clear denominators pretty easily, and we'll see that we have DE over EF quantity squared equals DE over EF plus 1. So in other words, we've got a quadratic equation that is satisfied by our goal ratio. But I'll let you guys finish that off with the quadratic formula, or maybe just recognizing that that is the standard quadratic equation for the golden ratio. And we'll see that this ratio is in fact phi, the golden ratio. And that's a good place to stop.